Okay, so yesterday's uh, success criteria was that you could just differentiate between molecular formulas and empirical formulas. Today, what we're actually going to be able to do is determine empirical formulas based on the percent composition within the compound. If you remember, I was talking about percent composition. You remember that that's where we say what percentage of a compound is this element, whatever. So if you look at your packet that we're working on, this packet that is called Chemistry Empirical Formula Guided Inquiry, and you're looking at the back of the front page, look where it says Empirical Formulae, why do we need to know? And so what this says is when analytical chemists analyze an unknown substance, they don't know its molecular formula, but they can use their lab equipment to determine the elements and how much of each one are in a compound. Determining the empirical formula of an unknown compound is the first step to determining its molecular formula and identity. So how to determine empirical formulae? The subscripts in an empirical formula represent the ratio of atoms in a compound. We were just talking about that. What's the simplest ratio of the elements in a compound? For example, ethene's empirical formula of CH2 means that for every carbon atom, there are 2 hydrogen atoms. If we know the number of moles of each atom in a compound, we can determine the empirical formula. So example number 1, and there's some typos here, so you got to pay attention. But example number 1 says that we have this substance, the sample, its percent composition by mass is 80% carbon, which we're actually going to change that. So we're actually going to say it's 90% carbon like the rest of the problem does. So 90% of it is carbon, and the other 10% is going to be the hydrogen. Okay? So some of those numbers are a little different, like 80-20 or whatever. We're going to use the 90-10. So it's 90% carbon and 10% hydrogen. So step 1, all we got to do is determine what are the masses of those things then. Well, we don't know. It doesn't say how much of the sample we have, so we can't say 90% of this or that. We can't do it. We don't know how much we have. But what we can do to make things really easy in step 1 is assume that we have 100 grams. Because if we assume that we have 100 grams and 90% of it is carbon, then that means the carbon would have a mass of 90 grams, right? And if we have 100 grams and 10% of it is hydrogen, then the hydrogen would be 10 grams. So that's the first step. Really, you're just changing the percentages to grams. We're assuming that there's 100 grams. We'll pretend, all right? Because if we had 100 grams, that's how many grams of each we would have. Step 2, we're going to find the moles of each. Okay? So carbon, we know that we have, so let's do carbon first. For carbon, we have 90 grams. I wish I could figure out how many grams were in a mole, because if I knew how many grams were in 1 mole, I could then figure out how many moles this is. Can we figure out how many grams are in a mole? How do we do that? How do we figure out the number of grams that are in 1 mole? The molar mass. That's what the molar mass is, right? The number of grams in 1 mole. So how do you do that for carbon? It is. Is it not coming through? Huh? Well, let's look at the periodic table because that's how we do mass. So if I look at the periodic table and I look up carbon, it tells me that carbon has 12.01 grams in a mole. Okay? So carbon is 12.01 grams per mole. So if I know 12 grams is 1 mole, how many moles is 90 grams? Well, how many times does 12 go into 90? Or another way of putting it, what is 90 divided by 12? Set up the problem the way we usually do. Write down what's given and put it over 1. And if I have grams on top, then I know that grams have to go on the bottom here, right? So we just looked at how many grams are in a mole, and the reason why is because we're going to use that right here. Now, I think on the worksheet they gave an example of just 12.0. If you want to use that, that's fine. And that's how many grams are in a mole. That's what that conversion factor is. So the grams cancel out, and I'm left with moles, which is cool because that's what we want to try to find. This is telling me that right here, right now, if I solve this problem, I'm going to find out how many moles I have. So it's 90 moles divided by 12.0. All right. And if we do that, put it in the calculator, 90 divided by 12, you should come out with 7.50 moles. So that's how many moles of carbon we would have. Does that make sense? We've been working on this. We've been practicing this, right? So far, so good. Cool. For hydrogen, we have 10 grams. So I'm going to put that over 1. And again, if I have 10 grams, how many moles is it? So we need to know how many grams are in 1 mole of hydrogen. And hydrogen is, according to our periodic table, 1.01. For the sake of just doing this example, I'll put down 1.0. So 1.0 grams per mole, just like we did carbon, but with a different molar mass and a different starting number. And here I'm going to end up getting 10.0 over 1, which is going to come out to be 10 moles. All right? So that's step 2, is find out how many moles of each thing you have. So all this empirical formula stuff, we're thinking about ratios of one type of atom to another. So what this is telling me right now, by finding that, and it's telling me that the ratio of C to H is 7.5 to 10. All right, but now that's not a very cool ratio. We like our ratios to be whole numbers, so that it looks like a real formula telling us the number of atoms of each type. We're not going to say you have 7.5 atoms of carbon. What does a half an atom of carbon mean? So we got to fix this a little bit. All right. The easiest way to make this a smaller ratio is we're just going to divide both numbers by the smallest one. And that's step 3, or step 3. Okay, so if I do that, I'm going to be able to make a simpler ratio. Ooh, don't want that. All right, so the C is just going to be 1, which we don't write 1 as a subscript, right? 7.5 divided by 7.5 is going to be 1, correct? Does everybody agree with that? For the H, we're going to have 10 divided by 7.5. So if I do that, 10 divided by 7.5, it comes out to be 1.33. Okay, so now we made a much simpler ratio, but the problem is here, and a lot of times, I'll be honest, a lot of times, this gives you the empirical formula and you're done. But we've got a little bit of an issue here, because this number is 1.33. We're still dealing with the same problem we were dealing with over here. We have a decimal. We can't use the decimals. We got to make them whole numbers. So if you run into this problem at all, start trying to double them, or triple them, or quadruple them, or 5 times them, or 6 times them, until you still have a simple ratio, the simplest that can't go any further, but you have whole numbers. Okay? So if I look at this, if I just double each one, then the empirical formula becomes C2H2.66. Still a problem. If I triple them, it would be C3, and then H would become 3.994. All right, close enough. All right, so this is actually going to be our empirical formula. And that's what we're doing. That's what we're working on today. Okay? So just run through it real quick again. Step 1, we just change those percentages to grams. We're assuming that there's 100 grams. Step 2, find the number of moles of each. Voila. Step 3, take the smallest number of moles and divide it into the others to get a simple ratio. Step 3b, if it doesn't come out to be whole numbers at the end, double them, triple them, whatever you got to do to make them be very close to whole numbers. All right? Might not be exactly, but if you get it in somewhere in the 0.9, 0.95 range, maybe slightly over 1 or whatever it is, but pretty close to being able to round it off, go for it. If it's something like you come across 1.5, 0.5, don't round that off to 2. Okay? Don't round it 0.5 off. Don't round 0.6 or 0.4, 0.7 or 0.3. You can round off 0.9s and 0.1s, but don't go further than that. All right? So that's what we're going to be working on today.